All right, so in the last video, we basically had a big review session for polynomials. So then let's actually go to the examples here. We'll do a few of these. Maybe we start with example 29. And let's graph this thing. So I'm just going to fill in the information, and then hopefully that'll be enough to graph it. What's the leading coefficient here? The leading coefficient is 1, positive 1. What's the degree? The degree is 2. Awesome. So already I have a positive leading coefficient and an even degree. So this should already tell you what the end behavior is going to look like. So I'm just going to kind of sketch it in. I know that the end behavior will look something like this. Awesome. When I ask you specifically for the end behavior, I don't want you to just draw two arrows. I want you to mathematically denote what the end behavior of this function is. So let's talk about that. To write the end behavior, if you were in on-level pre-cal, you may have written it like this: as x approaches infinity, y approaches infinity. So as x goes further to the right, y goes further up to positive infinity. And as x approaches negative infinity, y approaches, and then so you realize that, okay, as x goes farther left, y goes farther up to positive infinity. So that's how you would have written in behavior maybe last year if you were on level. How we're going to write in behavior this year is going to look a little different. So here's how we write in behavior. The limit as x approaches infinity, so it looks like lim and then x arrow infinity, so that's where kind of this piece goes to, of f of x equals infinity. So that's where this answer ends up. So that's the far right in behavior. The limit as x approaches infinity of our function f of x is equal to infinity. We would do the same thing for the other side. What's the limit as x approaches negative infinity of f of x? And that the limit as x approaches negative infinity was positive infinity. Okay, so that's how we're writing in behavior from now on, and we'll get a lot of practice with this in the next few examples. Okay, what's the y-intercept of this function? The y-intercept is the point 0, comma what? Well, if you plug in a 0 for every x, you get 16. So the point's 0, comma 16. Okay, and again, these are sketches. These are not perfect graphs. So as long as you label things correctly, I'm not going to worry about scaling or anything like that. So the y-intercept is the point 0, 16. Leading coefficient 1, degree 2. The last thing, what are the zeros and their multiplicity? Remember, this is always the hardest one. This is the one where you have to set the function equal to 0 and solve for x, usually by factoring. Now, luckily for us, this is a quadratic, and this quadratic will factor nicely. Remember, when you factor quadratics, what multiplies to the last number adds to the middle number if the leading coefficient is 1, and it is. So this is going to be x minus 4 times x minus 4. Or we would write x minus 4 squared. So then what are the solutions here? Well, if you set the one factor, x minus 4 equal to 0, you're going to get x equals 4. Okay? But because of this power to which it is raised, it has a multiplicity of 2. A multiplicity of 2. So this means it's going to bounce. Even multiplicity. It's going to bounce off the x-axis at positive 4. So 1, 2, 3, 4. We're going to bounce here. Okay? So let's connect the dots now. So remember, originally I put these, so these just indicate in behavior. So actually, it's probably going to look something like this, because we know it crosses through the y-axis at 16. It bounces off the x-axis at 4, and looks something like this. Okay? So I was a little off where I put my arrow, but that's okay, right? And so this is our quadratic, this parabola right here. Awesome. Next example. A little bit faster pace now. The leading coefficient is -3. The degree is 4. So we have a negative leading coefficient and an even degree. So maybe over here, that way I don't have errors in my graph, I just kind of indicate to myself what that's going to look like. The negative leading coefficient means we're looking at a downward trend, but the even degree means they point in the same direction. So both are pointing down. So already I can think about my into behavior, which remember is always the limit as x approaches infinity of f of x equals, and then you're going to answer that question, and the limit as x approaches negative infinity of f of x, and you're going to answer that question. So what do we have here? What's going on? Well, as x approaches infinity, so as my x values get bigger and bigger, that is, as I go further and further and further to the right, the further right I go, the further down the function's going to go. When I draw this, it's just going to go way down and to the right towards negative infinity on the right-hand side. What about the left-hand side as x approaches negative infinity? So as x gets infinitely more negative or more to the left, what are the y values doing? Well, as you go further and further left, just like on the other side, the y values are going further and further down to negative infinity. There's my end behavior. What's my y-intercept here? Remember, y-intercept is a point. It's the point 0, comma something, where that something is what you get when you plug in a 0 for every x, and I think you'll all agree that the value I get when I plug in a 0 is 0. So cool, I know for a fact it crosses through the origin. Okay. Finally, what are their zeros in multiplicity? So we're going to set the function equal to 0 and solve for x. Sorry, these should be on the next page, so these are... Okay. Set this equal to 0 and solve for x. Negative 3x to the 4th minus 12x cubed. Well, this isn't a quadratic, so I can't factor it by the means we used here. And there's not like 4 terms, so I can't factor by grouping. So we are still going to factor this, but we're going to factor this by a greatest common factor. A greatest common factor. So think for a second what that greatest common factor would be. And it's going to be negative 3x cubed. I hope you agree. Negative 3x cubed. If I factor out a negative 3x cubed from here, I'm left with x plus 4. Okay. You can always check if you factored out a greatest common factor correctly by redistributing it back in and seeing if that's what you get. And indeed we will. Okay. So we haven't solved it. We've factored it. Great. Now we're going to set each factor equal to 0. So here's a factor. If I set x plus 4 equal to 0, I get x equals negative 4. So that's where it's going to cross the x-axis. I always want to give the 0 and multiplicity. So what's the multiplicity of this factor? By definition, multiplicity is the power to which it is raised. So the multiplicity here is 1. That's an odd number. So I'm going to put a big C here because this means it's going to cross through the x-axis at negative 4. Cool. A lot of people forget this step, but x plus 4 is a factor, but negative 3x cubed is also a factor. It was our greatest common factor. So we're going to set that equal to 0. Okay. And it won't take you very long to realize what x has to be here in order for this to equal 0. But if you divide both sides by negative 3, 0 divided by anything is 0. And then take the cube root, you're going to get x equals 0. Maybe you knew that just by looking at it, I hope. We get x equals 0. But just like any factor, it has a multiplicity. What's the multiplicity of this factor? Well, it's the power to which it's raised. The multiplicity here is 3, which is also an odd number. So again, I'll put a big C here to indicate that it will cross through the x-axis at 0 as well. Okay? And that's everything we're going to need here. We know it's in behavior, pointing down and to the left and down and to the right. We know it comes up here, it crosses through the x-axis. At some point, it's going to have to turn around so it can cross through the x-axis again. There's no other turning point because there's no other x-intercept over here, and it's going to fall in line with my in behavior. So it might look something like this. Okay. Again, these are sketches. The graph may do all kinds of cool stuff up here. We don't know. It could have several turning points, whatever. We're not sure. The only thing we know is how it ends as far as its in behavior. We know its y-intercept and its x-intercept and their multiplicity. So we're going to get a graph that looks like this. All right. We'll do 31 and 32, and then I'm going to leave 33 up to you to check your work against the key. So much faster now here. With x cubed minus 9x, the degree is 3, the leading coefficient is 1. The y-intercept is the point 0, 0. Plug in a 0 for every x. The x-intercept's here. Picking up the pace significantly. I'm going to solve this equation, 0 equals x cubed minus 9x. I'm going to factor out an x. And I'm going to factor that difference of squares there, x squared minus 9. I'm going to set each factor equal to 0 and solve. This one I'm going to get x equals 0, pretty easy. If I set x minus 3 equal to 0, I'll get x equals 3. And if I set x plus 3 equal to 0, I'll get x equals negative 3. Notice each of these has a multiplicity of positive 1. It's assumed and understood that they're all being raised to the first power. So the multiplicity of each of them is 1, which is of course an odd number, which means we're crossing through the x-axis at each of these points. So let's go back up here. Of course, we've known from the y-intercept that it was crossing here. It's crossing at positive 3 and at negative 3. And because of our in behavior, a leading coefficient that's positive and a degree that's odd, we should expect this kind of look. So let's do that. Drawing things in. Crosses through. Has to turn around so it can cross through. Has to turn around so it can cross through and then eventually fall in line with our predicted in behavior. Awesome. I'm not going to write the in behavior, but hopefully you agree that the limit as x approaches infinity is positive infinity. As x goes further right, the graph goes further up, and the limit as x approaches negative infinity is negative infinity. Okay. So I'll let you practice writing the in behavior in our new notation. Okay, so let's look here. Because this is in factored form, it's actually going to be easiest to find the zeros. They're kind of already basically given to us. Let's look. If we set that equal to 0, x minus 2 cubed times x plus 3 times x minus 5, well, looks like the problem's kind of already done the hard work for us. It's already factored. So we're going to do what we know to do, which is set each factor equal to 0 and solve. There's 3 factors here. If I set x minus 2 equal to 0, I'm going to get x equals 2. Awesome. Here I'll get x equals negative 3. Setting x minus 5 equal to 0 and solving gets me x equals 5. What's the multiplicity of each? Well, 1, 1, and 3. So this has a multiplicity of 3. This has a multiplicity of 1. This has a multiplicity of 1. Remember, multiplicity is just the power to which the factor is raised. All of those are odd numbers, so that's a cross through at every point. Remember, if this multiplicity was an even number, like a 2 or a 4, then it would bounce off the x-axis at that point. Okay. So then the next thing we have to consider are the harder ones, which are these y-intercepts and the leading coefficient and the degree. So the y-intercept here, remember y-intercept is what you get when you plug in a 0 for every x. So let's look at that. That's going to be, so I'll just write it out, 0 minus 2 cubed times 0 plus 3 times 0 minus 5. 0 minus 2 is negative 2, and negative 2 cubed is negative 8. 0 plus 3 is, of course, 3. And 0 minus 5 is, of course, negative 5. Negative 8 times 3 times negative 5. Well, negative 8 times negative 5 is positive 40. And 40 times 3 is 120. So this is a y-intercept at the point 0, 120, which is way up here at 120. Okay. And with our x-intercepts of positive 2, positive 5, and negative 3, we're pretty close to having this thing whooped. Obviously our scale's way off, right? If this is 3 and 2 and 5, then the 120 is like way up there, but that's okay. We'll just kind of label everything. Okay, so then the last thing we need is our in behavior, so we can know how do we connect these things. Is it starting way up here and coming down? Let's look. Well, the leading coefficient and the degree are not quite as clear because this has been factored. If we were to multiply everything out, we could get going, but that's a little bit more challenging than what we need. All we're really going to do is we're going to take the first term of each of these factors and the power of each of these factors and just multiply them out. So we have x cubed times x to the first times x to the first. That's going to give x to the 5th power. So instead of having to multiply all of this out, we can find our leading term by using that trick, taking the first term, raising it to the power given, and then for each one, and then multiplying, you're going to get x to the 5th. So that's going to be a degree of 5 with a leading coefficient of positive 1, which with that positive leading coefficient and odd degree, we should expect this kind of behavior. And that's all we need to have a nice sketch. Remember, it crossed through each of these points. Very nice. So there's this again, I'll let you practice writing the in behavior. Hopefully you agree that the in behaviors for both of these are the same. I'll have you do this example on your own. So try this one on your own and then test your work against the key. In the next video, we'll look at these factoring examples and then be done for the day.